Hello, and thank you for coming to the Frontiers of Physics lecture series. Great turnout tonight. It's very gratifying to see so many people interested in physics, and I think I recognize some of you now. Let's see, is the high school class from Port Angeles here? Yay! So my name is David Kaplan. I'm a professor of physics, a particle and nuclear theorist in the department here. I want to welcome you to the Frontiers of Physics lecture series, which is funded by a generous donation by Drs. Patrick O'Hara and Katrina Randolph. Without their help, this wouldn't have been possible. It all started with an email I got from somebody I didn't know saying, how would you like to have a public lecture series to share the excitement of physics? And from there, it led to this. So we've had many great lectures. If you didn't make the past lectures, we've had lectures from Lisa Randall, professor at Harvard, talking about dinosaurs and asteroids. We've had John Preskill talking about quantum computing, David Charbonneau about habitable planets around other stars. We've had Nobel laureates, David Gross, David Wineland, and Ray Weiss, who told us about gravity waves. And next October, our speaker is going to be a doctor from Caltech named Sean Carroll, who's written many popular works and is a great speaker. And his topic will be on the many worlds of quantum mechanics and how it can help us understand the emergence of space-time. So the University of Washington, as I'm sure you know, is a driver of the culture of the area and the economic engine as well. Physics plays an important role in the university. Our department's won 2 Nobel Prizes by Hans Dehmelt and David Thalles, and there are many prize-winning faculty doing top research. You may think that we're well supported since we're a state university, but you may the state actually supplies 5% of the operating budget of the university, so we have to operate very much like a private university, which means that if we want to stay a top university, we have to innovate, and if we innovate, we need public support. Right now, one of the key initiatives we're trying to push through in the physics department is called the Thalles Institute for Quantum Matter. This is an institute that will work on quantum materials and quantum information science, quantum computing, things that could completely transform our lives and help with local industry turn Seattle into a hub for the new quantum technology age. And we need help getting this off the ground. It could be at many different levels. It doesn't have to be something like the Allen School of Computing. If you can't give it that level, there are many different ways to do it. In fact, just this year, somebody last year gave us some money to give extra graduate student stipends. $5,000 or $10,000 can entice a graduate student who might otherwise go to Harvard or MIT. And we were very successful at recruiting great graduate students using these stipends, including a record number of women and underrepresented minorities. So we're very happy with participation at any level. But even if you can't donate anything, but you're really interested in physics and would like to see what experiments are going on or talk to physicists, you should contact us. There's a misperception that you have to say something really smart if you're going to talk to a physicist. But I know from personal experience, if you go up to a physicist and you say, "What are you working on?" they'll think you're brilliant. So today's lecturer is Paul Steinhardt, professor from Princeton. He got his undergraduate degree at Caltech, working with Richard Feynman. He got his PhD at Harvard in 1978 with Sidney Coleman, who was a wonderful physicist who was a perfect blend between Groucho Marx and Albert Einstein. And then he went on to the Harvard Society of Fellows. He was a professor at the University of Pennsylvania from 1981 to 1998. And then he was hired by Princeton, where he is presently. And in 2001, he was made the Albert Einstein Professor in Science. They don't have a God of Science chair, so this is as good as it gets. He's currently director of the Center for Theoretical Physics at Princeton. What makes Paul really unusual is that he's made major contributions in 2 completely different fields, cosmology and condensed matter physics. In condensed matter physics, he pioneered the theory of quasicrystals. These are amazing crystals that have 5-fold symmetry and no translational symmetry. And if you want to see what they look like, you can go to the physics building. They're stenciled on the windows of the stairwells. For this, he got the Buckley Prize, one of the top prizes in condensed matter physics. And he recently, well, he not only came up with a theory, but then he wanted to find out whether they existed in nature. And that led to a hunt that eventually involved an all-terrain vehicle through the swamps of Kamchatka Peninsula. And so if you want to read this story about physics meeting Indiana Jones, he just wrote a new book called A Second Kind of Impossible, the quest for a new form of matter. And this is on sale at the bookstore. Today's lecture, though, will be about his other great contribution, which is in cosmology. Back in the early 80s, he's one of the inventors of inflation theory, for which he won the Dirac Prize, along with other co-founders of the theory. But like a great physicist, he started questioning the theory as it grew up and morphed into something different than what he had originally thought it would be, and then started tearing it down and building up something new. And this really now takes you out of textbook physics to the real frontiers of physics where people disagree. A lot of great physicists on both sides of the issue will argue about what actually happened in the early universe. And not only that, but where is the boundary between physics and metaphysics? And so this is what the topic of today's lecture is. So let's welcome Professor Steinhardt.
Well, good evening. It's a great pleasure to be here. A wonderful honor to be invited to take part in this lecture series, which has had so many great speakers in the past. And I'm so glad to see so many of you out here this evening. There's no question about what we're going to talk about this evening. 1 second, I have to get my thing to work. Yes. There's no question what we're going to be talking about this evening. It's right there in the title of the talk. We're going to be addressing this question. What really happened 13.8 billion years ago? Now, had I entitled it 13.8 million years ago, the chances are that many of you would not be here tonight. Because I don't know about you, but I don't know anything special that occurred 13.8 million years ago. But 13.8 billion years ago, that's a really important time for all of us. Because we all know that that is the time when the space that eventually evolved to be our universe, the universe we observe today, first began to expand, full of a hot gas, full of elementary constituents that over the 13.8 billion years expanded and cooled to form the universe we observe today. The chances are, if I had taken a survey when you came in the room, how you would answer this question, I think most of you would say, I know the answer. The answer is what happened then was the Big Bang. And by that, I think you would mean the sudden creation of the universe from nothingness, from no space, no time, no matter and energy, into suddenly this space full of hot, expanding gas. And in fact, at the present time, most of my colleagues in astronomy and astrophysics and many other areas of physics also take this same point of view. But as David emphasized, my job here tonight is to represent the frontiers of physics and what's happening at the frontiers of cosmology among those who, like me, who think hard about trying to create a strong and effective and powerful theory that explains the properties of the universe. There's growing doubts about this Big Bang idea. And there's been increasing interest in an alternative possibility, a possibility in which space and time didn't spring into existence at all 13.8 billion years ago. It already was. And instead of being a creation moment, it's a moment of transition, a transition from a period of contraction to the current period of expansion. And the key events that occurred prior to this transition, what we call this bounce from contraction to expansion. The key events that occurred during this period of contraction are the events that set up all the large-scale properties of the universe that we observe today, including those properties that are responsible for our existence. So we're debating today which of these ideas is correct, and I'm not going to reach a conclusion. That's not my point. My point is to try to explain to you what the debate is about, why there are these different points of view. And then leave it to you to decide what you think on the way out the door. How would you answer the question next time you hear it? So, we're trying to explain the universe. There's certain things we know for sure about the universe that any good theory, no matter what you're thinking of, has to explain and be consistent with and has to fit. The first is that if you look at the composition of the universe today, it's actually pretty complex. It doesn't just consist of the kind of matter that we know of, matter made of atoms or subconstituents of atoms. In fact, that kind of matter only occupies about 4% of the stuff of the universe, of the energy of the universe today. There's another form of matter which is unlike that atomic matter, something strange, something we don't quite know what it is. The only thing we know about it is, number one, it doesn't scatter or emit light, and so that's why we call it dark matter. And the other thing we know about it is that, like ordinary matter, it tends to gravitationally clump. So if you put a mixture of matter and ordinary matter and dark matter together, they'll tend to clump together. And this dark matter plays a crucial role in the history of the universe. If you suddenly took the dark matter out of the equation, you wouldn't end up with a universe that looks like ours at all. In fact, at this time in cosmic history, there wouldn't even be galaxies and stars as we know it. So we are our existence to this dark matter. Our past depends upon dark matter. Our future, though, depends upon the nature of dark energy. Dark energy today occupies 73% of the stuff of the universe. And unlike atomic matter or subconstituents of atoms, unlike dark matter, it doesn't gravitationally clump. Its effect on gravity is the opposite, or gravity's effect on it, I should say, is the opposite, which is it tends to speed up the expansion of the universe. It has a kind of gravitationally self-repulsive effect that actually speeds up the expansion of the universe. And we observe this speeded up expansion in the universe today. We don't know what this dark energy is. It could be some sort of constant source of energy associated with empty space, a so-called cosmological constant. Or it could be some kind of energy that is slowly varying with time, and therefore our future will be rather different than it appears to be today. These are issues that are going to come up in the debate we're going to be talking about this evening. The other thing we know about the universe is that when we look around us now with powerful telescopes, that it's lumpy. The lumps occur on all scales. There can be small lumps like dust particles. There can be rocks. There can be larger asteroids. There can be planets. There can be stars, solar systems, galaxies, clusters of galaxies, superclusters of galaxies. A lot of complex structure exists in the universe today wherever we look around us. That's today. The other thing we know about the universe is that if you go back in time, remember it's expanding, so if we go back in time, when it was about 1,000th of its present size, it didn't look like that at all. In fact, it looked something more like this. This is effectively a snapshot of what the universe looked like when it was about 1,000th of its current size. It's a temperature map. It's a measure of the temperature across the sky, but you could just as well view it as a measure of the concentration of matter or the concentration of energy. It is measured with a pretty precise camera that's able to measure temperature to within a fraction of a degree. Blue represents 0 degrees or absolute zero. Red represents 4 degrees. But you might notice that you don't see any blue and red. You just see pink, and that's because the universe at that time was extraordinarily uniform. One of the most uniform things ever observed, with a distribution of temperature that was 2.7 ... degrees above absolute zero to at least 4 decimal places. And our existence grew out of this extremely uniform universe. Our lumpiness grew out of this extremely uniform universe. The theories that we'll be talking about tonight all agree about how we go from this extreme uniformity to the lumpiness we observe today. And they also agree on what the composition, the relative composition of the different forms of matter and energy were at this time and what they are today, and how one got from one to the other. So where do they disagree? Well, they disagree on where did this simple universe, original universe, come from, this one that was extremely uniform. How do we get from some beginning or some transition or some bounce to this condition? Now, in trying to deal with that issue, there are two things a theoretical cosmologist has to struggle with. The first is quantum physics. Quantum physics hates uniformity. Quantum physics is inherently a phenomenon which creates fluctuations. Even if I just have a single particle like an electron that I try to put on the tip of my finger, which according to the rules of Newton, I could do easily, the laws of quantum physics, you say, no, you're not allowed to do that. You can put an electron on your finger in such a way that on average it's on the tip of your finger, but actually if you ask where it is at any given time, or you try to test where it is at various times, you will find that it's actually constantly quivering and wavering and fluctuating. And so it is with space. If you try to create a space which is uniform, and quantum physics is playing a large role in the process, is dominating the universe during that process, it's going to struggle against that smoothing, because space itself is something that's subject to quantum physics. It can also wiggle, curve, warp, and twist, much like shows in that diagram over there on in the inset. And the Big Bang is supposed to be the ultimate version of this quantum dominance, this period when quantum physics dominates over the predictive laws of the more predictive laws, like the predictive laws of physics, and causes space itself to wiggle and warp in this way. So somehow, this is the opposite of what we're looking for. We're trying to make a smooth universe, and quantum physics is trying to unsmooth it. The other problem we have to deal with in cosmology is time. If the universe has a beginning, let's say a Big Bang, and if that Big Bang is dominated by quantum physics, so coming out of the Big Bang, the universe is about as irregular as you could imagine it could be, you have to somehow make it smooth. And you have to make it smooth over a large region of space. And that takes time. And that takes some kind of synchronicity for such a thing to occur. Time is essential for smoothing, and we have to smooth it if we have a Big Bang. So we might imagine an analogous problem. Another problem of smoothing would be, for example, suppose you owned a bookstore with a large space for your store, and you want to bring in this crack team of carpet layers in to lay carpet in your store. But suppose you're rather perverse in your instructions to them. You're only going to give them 10 minutes to lay the carpet in your store. So you're going to give them a key. They're going to enter the store at 7 a.m. 10 minutes later, you're going to come in with a cup of coffee, or I've gotten your cup of coffee, and you expect that carpet to be laid, and you expect it to be laid perfectly. Well, you can imagine what might happen. The carpet laborers will rush in at 7 a.m. They'll rush out to different sections of the store, each smoothing their little part of the rug, but there's no time for them to communicate with one another. So in fact, when they come together and try to complete the process, well, the likely outcome will look something like that. It will be a disaster, and anything but a smooth carpet. Just like if we don't give the universe enough time, coming out of a quantum-dominated Big Bang, we'll get anything other than a smooth universe, because time is essential for smoothing the universe too. If the universe has a beginning, like a Big Bang, we can actually compute from our laws of physics the maximum space over which space can have smoothed. And it has various names. We sometimes call it a Hubble radius. That radius would be a radius of a volume, which would be the smoothing volume, the largest volume over which you could possibly have something smooth at a given time. It's named after Edwin Hubble, who's a famous American astronomer who discovered that the universe is expanding. It's also known as the Hubble horizon. The Hubble horizon because it's also related to what's the maximum distance you can see in the universe at a given time, given that time had a beginning and that light can only travel at a finite speed, and other forces can only operate at a certain speed over a certain distance. For tonight, I'm just going to call it the horizon. So when I say the horizon, I'm talking about this region. And if we go back to a time when the universe was 1,000th its present size, the size of that horizon would be about the size of that blue circle. So we wouldn't be surprised to see the universe smooth over regions that are that small. But we would not expect it to be smooth over the huge scale we see today. So we can imagine smoothing, let's say, in one region or another region or another region, another region, just like our carpet layers could smooth locally around where they were working. But when it all comes together, what we should expect when we look on larger scales is that the connecting space between them should be very non-uniform. Okay, so what that means is that if we're coming out of a Big Bang, which is dominated by quantum physics, which necessarily makes things as rough as imaginable, it means that to find a smooth universe seems impossible. There's just not time to make it. Yet, when we look out at the universe, when we gather light from this period when the universe was 1,000th of its present size, light that we call the cosmic microwave background, we observe it to be this extraordinarily smooth universe. So it's the same as if we showed up after 10 minutes after our carpet layers entered the room. It's as if we came back after 10 minutes and we found that instead of looking like this, the rug was perfectly smooth. How in the world did the carpet layers do that in 10 minutes? How is that possible? So the simple Big Bang theory, the idea that was first emerged in the 1920s and was developed over a lot of the last century or so, that idea was just a simple Big Bang, doesn't seem to do the trick, doesn't seem to explain this fundamental fact about the universe. So we have to look for inspiration. How did our carpet layers possibly solve the problem? We might look for inspiration to DC Comics. Why not? Here's Plastic Man. You may not know about Plastic Man, but I think his name tells you what his characteristics are. He's super elastic. Now, according to Einstein's theory of general relativity, space is itself elastic. When we say space is expanding, or we say the universe is expanding or space is expanding, we really mean space is elastic. So it will appear that objects are moving apart from one another simply because space itself is itself stretching. But how elastic it is depends upon what kinds of energy the universe contains. Some kinds of energy, like ordinary matter and radiation, make space, I'll say, medium elastic. You can stretch it, the universe expands, but they tend to resist the expansion. So they struggle against the expansion. It's hard to get things to have rapid expansion. On the other hand, there's other forms of energy which can make space extremely elastic, super elastic, so that it's really easy to stretch it. In fact, it wants to stretch. Gravity drives it to stretch at an extraordinarily fast rate. So you can begin with a universe which is all scrambled and wiggly and quantum distorted, maybe like that, maybe like Plastic Man in this state. But if you can stretch it super fast, you can then take a small region of space and blow it up to a very large size in a very short period of time. And this idea is the idea that underlies inflation, the inflationary theory. Inflationary theory is basically Plastic Man on steroids. Because the idea of inflation is that shortly after the Big Bang, and you had this highly irregular universe, the universe became filled with a form of energy, a field that permeated space, that caused space to become super elastic and to stretch at an incredibly fast rate, so that it doubled in size every 10 to the minus 35th seconds, or every billionth of a second or so. And it continued that way for a short period. So you could begin with a universe which was extremely tiny to begin with, much tinier than you originally thought, and then stretch it to huge size. So you could begin smaller than the horizon, be smoothed out, and then stretch to large size. And you'd end up with a large, smooth universe. So it's as if our carpet layers came together and brought in a super elastic carpet. Elastic carpet that only occupied about that much size. They could all gather around it, and they're close enough that they could communicate with one another. They were inside each other's horizon, so they could synchronize and agree on how to proceed. And then, because it was super elastic, after agreeing on how to proceed and setting up what their plan was to work in sync, they suddenly ran apart from one another, holding onto the carpet, stretching it out in just a few minutes, stretching it to the sides of the room, placing it down, and voila, you have a smooth carpet. But there's a big problem with this idea. And it's kind of captured in the cartoon that you're seeing there, which is this plan depends upon really keeping everybody in sync. It requires that when you smooth things, everything, or in this case, stretching space or stretching Plastic Man, everyone's going at precisely the same rate. Now, in practice, if you tried to do this with Plastic Man, it wouldn't occur because people would inevitably get out of sync. And similarly with the universe, whether you like it or not, quantum physics doesn't let you keep things in sync. Quantum physics will insist that as the universe begins this super rapid stretching, not every direction will stretch in exactly the same way. In fact, there'll be some regions of space which, due to the quantum fluctuations, will stretch faster than the others, and some regions faster than that, and some regions yet faster than that. And so some regions will become enormous, so enormous that there's time for yet other quantum fluctuations to occur within that region to make part of that stretch even faster than the rest of it. And so instead of getting something regular, well, you're going to get something rather irregular. In other words, quantum physics, once again, spoils everything, including spoiling this idea of inflation. So that instead of getting a universe that looks nice and smooth and uniform, you get different regions of space which are in different stages, have undergone different stages of stretch. Most of that space is still inflating or still stretching in this super elastic way, even today. In this artist's conception, the black regions, the darker regions, represent the regions which are still stretching. It's not realistic in the sense that those regions should be exponentially larger than the regions which are not dark, because the darker regions, the ones that are still stretching, are continuing to stretch so fast. But even in the regions that do stop stretching, analogous to our carpet layers managing to lay down a few pieces of our carpet, even there's a tremendous amount of irregularity due to this quantum runaway effect, due to the fact that once you start stretching, quantum fluctuations will mess up your plan and continue to mess up your plan over time. What that means is that when you finally put the carpet down or you finally stop the inflation, what you'll discover is in that region is the properties depend on the details, the particular history of quantum fluctuations that occurred prior to inflation stopping or prior to laying our carpet down. And that's represented in this picture by showing you that, well, there are some places where you might see galaxies, but there are other places where you don't see things. In fact, this kind of quantum runaway produces an effect that we call a multiverse. It's a universe in the sense that all the space is connected, but a multiverse in the sense that every possible conceivable thing you can imagine occurs one place or another in this multiverse, this inflating universe. And it will continue to happen. Literally anything that can happen will happen, and it will happen an infinite number of times. So think about it. You were trying to make a theory that explained why our universe had certain properties, why it's so smooth, and why it has other properties that we observe, why it's not curved and warped. And what we discover instead is that this idea, Big Bang followed by inflation, doesn't produce that typically. In fact, what it produces is every conceivable possibility, every kind of space with all kinds of combinations of curves, warps, and distortions. Another way of saying it is we've created a theory that was meant to explain our universe, but in which the universe we observe is actually highly unlikely to occur, because everything else occurs as well. So it's as if you tried to make a theory to explain why the sky was blue, and then you came back with a theory that said it could be blue, but it could be red, it could be polka dotted, green, etc. It could be anything. That's really not an acceptable scientific theory, because there's no test or combination of tests that you can ever rule out such an idea, since everything that can happen will happen in this multiverse. Yet for a long time, this was in some sense the best idea going. And one of the arguments was that there was no answer to this question. Is there any other option? Is there any other way of smoothing the universe than this superelastic inflating possibility? Well, let's go back to our carpet one last time. We said time is essential for smoothing. We've ruled out the idea that the carpet layers came in with ordinary carpet and within 10 minutes laid it out and made it smooth. We ruled out the idea that they had this superelastic carpet, which they could begin small and stretch it, and after they were all in sync, stretched it out, because that led to them falling out of sync and then producing carpet which had different properties in different regions of the floor. So what other idea is there, possibly, for making the universe smoother? Well, one possibility is cheat. Cheat, okay, and how would you cheat? Well, since you gave them a key to your business, what they could have done is not first showed up at 7 a.m. when you expected. You saw them enter at 7 a.m., but that was not the first time they were there. They were actually there before. They came there in the middle of the night. They had plenty of time to smooth things out. And then, in order to impress you, they left, came back at 7 a.m., sat around, chatted, and when you came in at 7:10, you came in with a beautiful laid-out carpet. Okay, cheat. That's the way to win. That's a possible way to win. How can we cheat, in this particular case, how can we cheat time in cosmology? Well, the answer is that the picture we've been imagining is the one where we assumed that the universe had a beginning. There was a beginning of time, and that beginning was 13.8 billion years ago. What if that's not true? What if instead space and time existed beforehand? And what really happened is that space and time contracted, bounced, and then began to re-expand. It's like our carpet layers having been there before and having already smoothed the universe out. We have all this extra time now, plenty of time, for smoothing the universe before, well, now we'll call it not the bang, but the bounce. In fact, because the horizon size is related to how much time you have, what we can say is that the horizon size, if you go back before the bounce, is enormous, more than enough to encompass everything that we observe today and the space that we observe today. Then what happens is that there's plenty of time for the universe to be smooth. It contracts, bounces, and when it bounces, it's smooth. It is smooth after the bounce and remains smooth until late times, as we observe it to be 1,000th, when the universe is 1,000th smaller than it is today. That takes care of time itself. Just making more time, just changing from bang to bounce, already goes a long way towards explaining why the universe has the properties that it does. But it's not enough, because we have a second problem that we have to deal with, which is quantum physics. In quantum physics, as we said, if it ever comes to dominate the universe, if space suddenly becomes quantum dominated in the sense that space itself is wiggling wildly, then you get back to this unpredictability problem. Then you get back to a kind of de-smoothing. Quantum physics de-smooths rather than smooths. So if we go back to our picture over here, the potential source of problem here is that bottleneck, where space is contracted. And in many earlier ideas about contracting and bouncing universes that people have had over the last decades, many decades, the last century or so, a common problem has been at that bottleneck, quantum physics dominates. When space contracts to that degree, to such a microscopic size, one reaches a point where quantum gravity effects cause space itself to fluctuate wildly and de-smooth any smoothing process that occurred beforehand. So how do you get around that problem? Well, the answer, which several of us have been thinking about more recently, is to have the bounce, but have the bounce occur before the quantum physics dominates, before it gets down to that tiny bottleneck. That means that it bounces before quantum physics dominates. and it bounces in a smooth, predictable way, from contracting smooth space to expanding smooth space. To accomplish this feat, you once again have to think about what forms of energy would dominate the universe during the period that it's contracting. In this case, having a form of energy like inflationary energy that makes space act like plastic man, makes it super elastic, is a really bad idea, because while stretching elastic material tends to make it smooth, if you contract it, the opposite happens. So you don't want to use that form of energy at all. You can use something similar, some field that's permeating space, but permeating space in such a way that instead of making it super elastic, it makes it the opposite, super inelastic. Like another DC comic character, the Man of Steel, the man who cannot be crushed, and even though he's under the influence of intense contracting forces. This kind of inelastic energy rather, is also physically possible. You can use the same basic ingredients as for superelastic, you just change the forces a little bit that you imagine that the field interacts under. So what happens in this case is when the universe contracts, what happens is because it's super inelastic, it's very hard when gravity tries to contract it for it to undergo much contraction at all. If you were watching, for example, two beacons which were shining flashes of light at you during this contraction phase, even though they're contracting, you'd hardly notice any contraction at all, because space is hardly changing at all. It's hardly changing the distance between distant objects. Space is remaining spread out. What is happening is that gravity, instead of contracting space, is pumping a lot of energy into this super inelastic stuff. So that energy is rising very, very rapidly. This field is gaining tremendous amounts of energy compared to the amount of matter or the amount of radiation or the energy in stars or black holes that existed beforehand. That stuff has been spread out during the period of that stuff, it may be spread out, whereas this new form of energy fills in everywhere in space with a whole new form of energy. It continues this process while the horizon, the smoothing, the space over which we can smooth things, is contracting. That's the thing that's contracting, and it's contracting at a fantastic pace. Space itself is hardly contracting, but the horizon, the region of space over which things can be smoothed, is contracting very fast until it gets down to a very microscopic size. By this point, we reach the bounce, and when the bounce occurs, what happens is all this energy that's been building up in this highly stiff, inelastic material suddenly bursts and and bursts into a form of energy and radiation that we're familiar with. Ordinary matter, ordinary radiation, dark matter, etc. So we end up with a universe after the bounce, which is extremely hot, contains almost entirely energy which was created from the decay of this super inelastic field, and a tiny horizon, a tiny region over which it can be smoothed, but we don't need it to be smooth because it was already smooth during this period of contraction. Because as the super inelastic energy built up, because it's so incompressible, it just resists any fluctuations, any variations in it to a very high degree. Not completely, but to a very high degree. Good enough that when we continue the picture to when the universe is now grown in size to a size which is about 1,000th of its present size, we have a universe which is extremely uniform and a horizon size which is very small, just like we need to explain the universe we observe. Now, there is an added bonus to this picture, because although this contraction under this super inelastic form of energy tends to make things very, very smooth, even it cannot entirely resist the effects of quantum physics. Quantum physics can create tiny little differences in the rate of contraction from one region of space to another. And this will mean that if we, instead of measuring the universe with a camera which can only measure the temperature or density to a few digits of accuracy, if we get a more powerful camera that can measure tiny, tiny differences of 1 part in 10,000, we would see remnants of these tiny quantum fluctuations, and they would look something like this in their distribution. They would have been produced early during the contraction phase when the horizon was big and smoothing was occurring and quantum fluctuations were small, and they would produce only tiny differences in the temperature and density of the universe at different points in space. They would not produce the multiverse effect that we talked about. There's no quantum runaway because in the case of the multiverse, what was happening is that we were stretching the universe super fast, and small quantum fluctuations were leading to huge new volumes of space being created. Here what's happening is the universe is contracting. There'll be these little quantum fluctuations, but these regions are contracting. They will never grow to form huge regions of space that make the universe irregular overall. They will only produce tiny deviations in the distribution of matter radiation. Now, what I'm showing you is both a typical prediction of the model, but what would be a typical prediction of the model. But what I'm actually showing you is the actual data, that when we actually tried to measure radiation from when the universe was about 1,000th of its present size with very precise cameras, with very precise detectors, this is actually the picture we observe. Regions with hot spots and cold spots here of large sizes, and if we had a higher resolution camera, we'd measure hot spots and cold spots of smaller sizes, and so forth, down to hot spots and cold spots of all sizes. And an added bonus of this theory is that it can produce this picture, which agrees with what we observe, without producing the multiverse effect. So, to summarize, if we have a universe which is bouncing, which goes through a period of ultra-slow contraction caused by a form of super inelastic form of energy, you will not produce the multiverse. You won't have quantum runaway of that sort. You won't have a big bang. You'll have a bounce instead. And the bounce occurs before the universe ever shrinks to microscopic size, long before it shrinks to microscopic size. In fact, it hardly shrinks at all during its period of contraction. That means there'll be no part of the story in which quantum physics dominates, which means you have a theory which predicts in the ordinary sense exactly what happens. Once I tell you what the inputs are into the theory, you can actually calculate what happens without worrying about quantum effects dominating. So it's truly predictive in this sense. So when we say that this theory, for example, makes a universe that's smooth and flat, you can actually, on a computer, go back and begin with a universe with really wild variations in the temperature and density of radiation, and compute what happens when it undergoes this contraction with the super inelastic form of energy, and you discover it very rapidly, almost instantaneously, smooths and flattens it. And that's a true prediction of the theory. We can't say that anymore for inflation. Inflation will produce some regions which are smooth and flat, but it also produces infinite number of regions which are not. It also unambiguously predicts variations in the density and temperature of the universe, those small quantum fluctuations. It does that while also predicting something else, that while we produce variations in temperature and density, we do not at the same time twist up space the way wild quantum fluctuations can. If we were trying to produce those fluctuations under a condition when there was a very high concentration of energy, they would not only produce variations in temperature and density, they would also tend to twist up space. And those would produce what we call cosmic gravitational waves. Not the gravitational waves that come from the collisions of black holes and the like, but gravitational waves that come from from the universe, from the expansion of the universe under the influence of quantum effects that produce those tiny quantum fluctuations. In a contracting universe, you don't produce any of those cosmic gravitational waves. And why is that important? Because we don't observe them yet at the present time. Even though we've been searching for them with rather sensitive detectors, so far we haven't found them. And that's something that makes it very distinctive for any kind of model in which the universe had a beginning, and which everything that set up the universe was created when the concentration of energy was very high. Those would produce very large and visible gravitational waves. The fact that we don't see them is an indication or a sign that what set up the universe was some kind of low energy events, like what would occur in a period of slow contraction, when the universe was large and energy was spread out. That doesn't mean that's the end of the story about searching for gravitational waves. Although there are many experiments today trying to look for these cosmic gravitational waves, and so far they've found one, there is something to look forward to, which is there is a prediction of what are called secondary gravitational waves, which are formed later in the history of the universe, which the contracting theory does predict. And those are targets for future experiments. So the first thing is we shouldn't see the primary cosmic gravitational waves. Anything from that's produced in the very early universe, we should only see secondary ones produced in the later universe, a target for future experiments. And then there's something else novel that I wanted to close with, which is once you have this idea of a bounce, you're led naturally to another possibility, a novel possibility, a kind of cyclic universe. After all, you're probably already thought of the idea that if I can have a bounce in our past, why couldn't there be many bounces in our past? Why couldn't there be bounces in our future? That idea of a cyclic universe has been around for a long time in philosophy and also in science since Einstein's theory of general relativity. But the kinds of universe we've been thinking about in the past, which bounce, are universes in which, if we were following two distant objects in the universe, or just space itself, what we would expect to see is the space would go through periods of contraction, then expansion, contraction, expansion, contraction, expansion, so that the distance between two different objects would repeat in a regular way, so that the temperature of the universe would repeat in a regular way, so that the densities of black holes and galaxies would repeat in a regular way, so that the horizon, the distance over which we could smooth, repeats in a regular way. But if you have a universe in which the contraction is controlled by this super inelastic stuff, which prevents the universe from undergoing much contraction, you end up with a very different kind of cyclic universe. You end up with a universe in which the distance, the size of the universe, actually doesn't undergo through regular periods of expansion and contraction. The temperature does, the density does, the horizon does. But the distances, or the size of the universe, or any patch of the universe we might look at, is doing something more complicated or more subtle. It's undergoing a long period of expansion, and then a period of contraction where it hardly contracts. Then another long period of expansion, and another period where it hardly contracts. And another long period of expansion. Well, you get the idea. The universe, or in the sense of space, keeps growing on average from cycle to cycle. But if you can only observe what's within your horizon, and the horizon keeps growing and shrinking from the same large size to the same small size, you think you live in a universe which is the same from cycle to cycle, because anything you observe and measure seems to be the same from one cycle to the next. Let me try to represent that with an analogy. Suppose you're standing on a very large balloon. You're sitting in the center, in the top of the balloon. You can hardly see the character in this case, but she's surrounded by a cloud. That cloud is supposed to represent a fog, which limits her horizon, how far she can see. So we're going to watch what happens when the universe is undergoing a kind of regular bounces or regular cyclic bounces of the sort I was describing. So I'm going to show this little video twice. Once, I'd ask you to watch the balloon. The second time, I'll ask you to watch the horizon, the ring of clouds. So let's first watch the balloon first. So you see at first the balloon contracts and expands, but it expands by more. So it's contracted a little bit, expanded a lot. It contracts a little bit and expands yet more. Expands a little bit and then expands much more. So the balloon is getting ever larger. And you might look at the top surface of the balloon, it's becoming ever flatter. So space is becoming flatter, smoother during this process. The more you go, the flatter and smoother it gets. Now, is the observer aware of what's going on in this situation? Let me start the film again. Oops. This time, watch the horizon. Just watch the ring of clouds. It shrinks and it grows. Now, that's how much of space she can see right now and what she can see. Now it shrinks and it grows again. But to the same size. So as far as she's concerned, the universe from cycle to cycle, as far as she can see, because she's limited by horizon, is the same from cycle to cycle. Even though what's actually happening, what she can't see, is that space on the whole is growing from cycle to cycle. This kind of cyclic model is novel. I don't know that any kind of version of that has existed before, but that's exactly what this kind of theory ends up predicting. And it leads to added predictions and added advantages. I'll mention one of each. The added prediction is that the period that we're observing today, a period in which the universe is expanding, in fact expanding at an accelerated rate, according to this picture, is not forever. It's going to end in a reasonably short time. If the universe is 13.8 billion years old today, maybe twice or three times that would be a period over which this accelerated expansion will end. And what's happening is that the energy that's driving that accelerated expansion, this sort of plastic mind elastic energy, its energy is going to decrease until it hits zero. That dark energy is going to hit zero. When it hits zero, that causes the universe to change from expansion to ultra-slow contraction. It changes the nature of space from being super elastic to being super inelastic. And now the universe begins to contract. And this is a prediction of the theory, and something we might even be able to detect by various means through future experiments. An example of an advantage of this theory is that because space is never really contracting very much in this theory, it's expanding a lot and contracting a little, expanding a lot and contracting a little bit. An advantage is that we don't see a buildup of stuff from cycle to cycle. A problem with other earlier ideas about the cyclic universe is that during the period of expansion, you produce stuff like stars and galaxies and the like that adds to the stuff in the universe, the black holes in the universe, and also the disorder in the universe, the heat energy in the universe, what we call the entropy. And then when the universe contracts, if it really contracts to a small size again, all that stuff gets reconcentrated. So when it comes back together again, you don't have the same concentration stuff as you had before. And so you don't grow to the same size as before. You can't keep the cycling going because you keep adding more stuff. Each time you contract the universe to a point. In this situation, though, you produce a lot of stuff in the universe during the periods of expansion, but during the periods of contraction, well, first of all, you're hardly contracting it at all, and secondly, the horizon shrinks to a point where you could lose sight of it. So by the time you get to the bounce, you've lost sight of the old stuff. All you can see is the matter and radiation that was produced when the universe bounced, and the energy that was being stored up became matter and radiation. You lose sight of the old stuff, all you can see is the new stuff. You lose sight of the old entropy, all you can see is the new entropy. So far as you're concerned, there's been no change to the entropy compared to the cycle before, and this repeats cycle after cycle. So this solves a famous problem with trying to create a cyclic universe. How do you stop the entropy from building up? The answer is, the same time you're producing the entropy, you're also producing more space in which you can spread out. And you can't see that entropy once it's beyond your horizon. It also explains why, when the universe began to expand, it doesn't have a terrific amount of entropy. It only has a modest amount of entropy. And that's another fundamental problem of cosmology, which Big Bang model never explained. So to summarize, what I've tried to explain to you today is that we have some really interesting debates and really interesting new ideas regarding this question, what really happened 13.8 billion years ago. I hope I explained to you why the original Big Bang picture didn't work, because the quantum physics that dominates during the Big Bang itself leaves a universe which is unsmooth, and there's not enough time to make it smooth. I hope I explained to you also why adding inflation to the Big Bang doesn't help either, because quantum physics spoils things again. Quantum runaway causes inflation to continue in most of space. And where it doesn't continue, it leaves different regions of space having different properties. So there is no particular prediction to the theory. Anything is possible depending where you are in that space. It doesn't really explain why the universe is as it is today. Now, I should say that even though that's the case for Big Bang inflation, many of my colleagues in astronomy and astrophysics, or physics generally, still prefer this idea. One of my favorite colleagues at Princeton in astrophysics loves to tell me that he loves the inflationary theory. He's convinced it's the right theory. He hates the multiverse. Can't stand it. That can't be right. And I try to tell him, well, that's really nice that you feel that way. The only problem with that is we don't know how to create a model with inflation which doesn't also produce the multiverse. You can't have the theory you want. It doesn't exist. But that's a common struggle that we're having right now in the field and the source of debate. People like the idea without the multiverse. They wish they could get rid of it. They don't know how to. And then I thought, I hope I've shown you that there is another radical, well, or different possibility, which is space and time didn't have a beginning, that the universe could have undergone many, or perhaps even an infinite number of episodes of expansion and a little bit of contraction, more expansion and a little bit of contraction, etc. So this is a very interesting idea, which has its own predictions, which are so far in agreement and are true predictions. But it's still an early days. There's still many ideas to work out in the theory, more tests to be made, and there'll be tests and ideas that will be developed in the coming years. So let me close with just one last thought. I want to give a little credit where credit is due. In particular, many of the ideas I've talked about tonight were not developed by me or by me alone. A very important player in this is this brilliant young theoretical physicist, Anna Eös, who is the first person I know of who's developed an example of a set of equations that can describe how the universe can undergo one of these bouts without collapsing to a small point where quantum physics would dominate. And that's one of the key ideas that are essential to this idea. So I'll stop there and I'll ask for questions. Thank you.